So, good morning, everyone. I hope you are all off to a good start this week. And welcome to another wonderful, fun-filled day of fluid mechanics. Today, we're going to discuss topics associated with flow regimes and how the flow regime you operate under relates to turbulence and shear stress. So when we're looking at flow regimes, we're looking at one of three categories, which describes, in general, the nature of the flow and how it relates to shear stress and, by extension, frictional dissipation. And these regimes are laminar flow, transitional flow, and turbulent flow. Now, when we're looking at laminar flow, we consider this flow regime for what's considered low velocity fluids, or fluids that can be considered highly viscous. Oh, I got somebody. Or high viscosity fluids. With no lateral mixing. We can consider the fluid layers, i.e. the streamlines, exist independently.
You don't have to wear your mask.
I don't.
I don't think so. Not when you're sitting down.
And so when the velocity starts to increase, we start getting into a transitional flow regime where we start to see the presence of flow irregularities
You'll get used to it. I mean, this is your day one by yourself, so.
Guys, whoever is not mute, can you mute yourselves?
I muted them, don't worry. So we have to start to see the presence of flow irregularities, eddies, which results in slight lateral mixing. Of streamlines. If I could spell streamlines. And finally, we have turbulent flow, which we categorize as high velocity flow and a big important thing to discuss here is that shear stress becomes a function of density and independent of fluid viscosity. So we have these three regimes going from low velocity to high velocity. We start in a laminar regime, then we encounter a transitional flow regime, and finally a turbulent flow regime. One other important thing to note in terms of laminar flow is that shear stress is a function of viscosity. And it's independent of fluid density. And so that's a big delineation in terms of, as we compare and contrast laminar and turbulent flow, the shear stress becomes dependent on flow viscosity, independent of density. Then as we get into a turbulent regime, the dependence on viscosity drops away and the fluid density becomes an important parameter of the flow. So the next question then becomes, how do we characterize better word is determine our current flow regime? So does anyone have any ideas on how we identify the current flow regime of operation?
You could take the Reynolds number of it.
Okay, we can calculate a Reynolds number. There are a lot of ways we can define Reynolds. If we want to define it in terms of words, it's a ratio of flow convective forces over a fluid's viscous forces. So as you can imagine, when viscosity is important in terms of as a function of convection or flow, we have low Reynolds numbers, and as the convective forces begin to dominate, viscous forces begin to be less important, we get into high Reynolds numbers. So we can calculate it mathematically with one of several ways. The most common is a fluid density times the fluid velocity, which I'll just note by U, times the flow diameter dimension, which is, pipe diameter, over the fluid's absolute viscosity, mu. I can also write it as a function of fluid velocity times the pipe diameter over the kinematic viscosity, which is denoted by a kappa. And I can also describe it or define it as a function of the pipe diameter times a term called G over absolute viscosity, where G is equal to the fluid density times the fluid velocity, which is known as a mass velocity. And G becomes extremely important when we're talking about gases. So a lot of times when we're looking at gas and vapor flow and we want to look into Reynolds number for calculations, this third way is how we do it. So once we can calculate Reynolds number, once we know it, we can categorize our flow regime based off of a series of values for both laminar, transitional flow, and turbulent flow. So I saw in the chat in terms of the third formula useful. When is the third formula useful? this dg over mu is extremely useful for gases. We'll talk about that here hopefully in a little while in terms of why that's important. But if you're going to be calculating Reynolds number for gases, you're going to more often than not going to be using this third form of the Reynolds number calculation. So jumping back to this, looking at laminar, transitional, and turbulent flow, we consider fluid to be in the laminar regime when the Reynolds number is below or equal to 2000. We consider the flow to be a transitional flow when it's between 2000 and 4000. And we consider fluid flow to be turbulent when the Reynolds number is greater than 4000. Keeping in mind that these windows are approximations. And they're not set in stone. So these values I give you are engineering ballparks so that you can make reasonable assumptions based on the data that you have. So in terms of illustrating the nature of these flow regimes, I've got a good video that describes it pretty well enough that I'll go ahead and share it with you all. I don't think we need the sound for it though. So hopefully you guys can see this video as it starts. So in this video, we've got a fluid streamline being illustrated by this red dyed fluid within this pipe of the same fluid, it's just not dyed. And what they're doing in this video is they're slowly increasing the velocity. So here initially we're in the laminar flow regime. So that streamline exists pretty well defined. You notice that there's no lateral mixing. However, as the flow velocity increases, you start to see the transition from laminar to a transitional flow regime. And that's going to be evidenced by slight eddies and irregularities that form within that streamline. You start to kind of see the streamline moving up and down, or there's presence of small mixing occurring along that streamline. So at this point, we consider this to be transitional flow. That streamline is no longer as well defined as it once was. And now as the flow velocity continues to increase, we're going to move from this transitional flow regime into a more fully turbulent flow regime. And the biggest characteristic of this fully turbulent flow regime will be the disappearance of that streamline entirely. So as you can see, that flow velocity is increasing more and more, and the actual existence of that streamline and the visible evidence of that dye becomes more and more muddled to the point where you can only barely see it because the mixing rate is so high within the flow system. Yes. Claire, did you have a question?
Yeah, I did. So I remember
Oh, I can't
in
hear
the
you, Claire.
oh, let me see just a second. Okay, can you hear me? Can you hear
I
me
can't
now?
hear you. If you want, you can ask a question in the chat if you're having audio issues, and I'll be happy to repeat it for everybody in the class.
We can hear you, so we can repeat the question.
Anyone else have
if you can't hear
questions?
it.
No? Okay, so let's take a look at an example. I realized I should have left it on this PowerPoint just a little bit longer. So this one's not too bad. Get the brain working a little bit. Let's calculate the Reynolds number of a fluid with a specific gravity of 0.9 traveling through a 3-inch pipe at a velocity of 1.2 feet per second. If the fluid viscosity is approximately 3.46 times 10 to the minus third pound mass per feet second. So let's jump back over to our whiteboard and see if we can not do this calculation. So we have Reynolds number, or UD over mu. I see your question. I'll answer it after this example. And if I remember correctly, the fluid density was 0.9, or the specific gravity was 0.9. I'm going to assume the fluid is a liquid, which means the reference density is water, which has a density of 62.4 pound mass per cubic feet. The flow velocity was 1.2 feet. The diameter was 3 inches, or 3 over 12 feet. And the viscosity was 3.46 times 10 to the minus 3 pound mass per foot second. If we do that calculation, we should get a Reynolds number of approximately 4,900, which implies that this is turbulent flow. So in the chat, I had a question about the nature of turbulence, as well as the essentially range for a laminar transition and turbulent flow. I think Claire mentioned in this text that it says in transport textbook, they define turbulent flow as having a Reynolds number greater than 10,000. Some texts will define that range in over different areas for a number of reasons. The simplest, most straightforward reason as to why it would define it something so high would mainly be the confidence of the assumption. There could be many systems where you're operating more in a transitional sense between 4,000 and 10,000 versus a turbulent, but the issue is when you're looking at transitional flow, one of the big things that comes into play is the reliability of the assumptions that you can make and the calculations that you can do in terms of estimating shear stress and frictional dissipation. And so in the text and as we define it here, we narrow that range for transitional flow primarily because there's no easy way to perform reliable calculations with an assumption of transitional flow. And so you run into the issue of, well, if you make the window for transition narrower, you have a better essential zones for operation, and you don't run into many issues in terms of transitional flow assumptions. But at the same time, if that Reynolds number is a little too low, you have more errors than you might think. And so, yeah, I know this isn't a very short answer. Like I said, it really comes back to stability and reliability. of flow measurements and as well as what the actual fluid is doing within the system. Because at the end of the day, these windows are approximations. These aren't set in stone. You could have some fluids that express turbulence as low as 2,000 Reynolds number, and then you can have some fluids that express or operate in a way that you can consider it laminar up to a Reynolds number of 5,000. It really, it's hard to nail down definitively, but at the end of the day, we kind of have to go off of these rules of thumb and then make adjustments as needed. And so I give you these windows in terms of ways to make judgment calls in this class, as well as when you go on, but keeping in mind with that, that big asterisk of it's really more important of understanding the nature of these flow regimes, how they occur, and how you can kind of characterize them in terms of flow properties. Does that clear things up a little bit? If so, let's jump forward a little bit. And we'll talk about the implications of these flow regimes as it relates to turbulence. Now, when we're talking about turbulence, we're really looking at fluid flow defined by irregular fluctuations in velocity. And I mean that in both the sense of the magnitude of the flow velocity as well as the direction of a flow velocity. So visualizing turbulence, what we typically see if we're looking at, following a fluid particle along a flow through a pipe in a simple direction, we see that while there might be an average that we can use, and for the most part when we do calculations, we operate based off of some arithmetic mean, in actuality, that fluid has a highly irregular flow, which results in those mixings, the eddies, the vortices, as well as the shear that we experience during flow. And so one of the issues that arises a lot of time is as I said, we can't really describe a reasonable function that can model this or predict the behavior. So the best thing we can do is operate off of a series of values, which are averages, and develop either empirical models or analytical solutions to describe what to expect within these flow systems. And the definitions of our flow regimes is one of the most fundamental ways in which we can make our assumptions in terms of how to describe fluid flow as it occurs and how it changes as a function of several properties, both intrinsic and intrinsic in nature. And one of the reasons why this turbulence exists and it results in a lot of issues as a function of the presence of boundary layers. And we're going to talk about boundary layers, not a ton. However, it's important that we touch base on it when it comes to a few things, definitely as it relates to turbulence. And what I mean by boundary layers is I'm looking at a solid fluid interface. that interacts with a moving fluid. I think I had one other question show up in the chat. Let me take a look. Oh, Mitchie, that gap was just a space for organizational purposes. I'll take another look later and we can talk in office hours, but you don't need to worry about that. So let's look at boundary layers, how they form, and how they contribute to fluid flow as it relates to shear and turbulence. So if I have, a pipe wall here, and I have fluid entering this system, one of the things that's going to happen along this pipe wall is the fluid is going to interact with the solid interface, such that the fluid directly touching that solid interface is going to operate under a condition where the velocity is 0. This is called the no-slip condition. And it's a function of adhesion forces between the fluid and the solid surface. And so we consider that to the point where the fluid essentially does not move at that direct interface. Now, if we move just a little bit above that interface, we're going to have fluid that sits above that boundary where the no slip occurs. And so if the velocity is 0 right at the fluid solid interface, what do you expect the velocity to be close to that interface? Is it going to be large or is it going to be small?
It should be small.
I agree, it should be small.
Any ideas? Anyone want to take a guess? I got somebody in the chat. All right. So I've got, it would be a low velocity, and you are correct. So if the velocity here what flow regime would we expect to see very close to our solid fluid interface? All right, so I got something in the chat that says my speakers aren't working. So can you guys hear me okay?
Yes, we can.
Can you guys try talking now?
Can you hear us, Dr. Lopez?
You guys can hear each other, but I can't hear you. Is that what you're saying?
Mm-hmm. Yeah.
Interesting. That's a new one. You guys there?
Yeah. Can you hear
Okay,
us?
I can hear you now. Apparently when I muted my computer, it muted my headphones. So I apologize for that. Now I can hear you. All right. It happens. Okay. All right, let's jump back in. Thank you guys, and I apologize for the minor inconvenience. So the velocity is really small, close to that interface. So what can we assume in terms of the flow regime that's going to operate really close to the pipe wall fluid interface?
Laminar flow.
So we're going to have laminar flow at that close to the interface. And that's independent of the actual bulk fluid flow. It doesn't matter how fast the fluid's flowing. Close to the solid fluid interface, we have laminar flow, which means if we've got turbulent flow, if I'm going to just assume this is turbulent flow, I have some degree of laminar flow at the edge, which means eventually I'm going to have some degree of the velocity starting to increase, get closer and closer to the bulk. Velocity is smallish. And so I have turbulent transitional flow. And then eventually, I can have what I might see in the bulk, where this is going to be my bulk turbulent flow. And yes, I know this isn't the world's best artwork. Which means I have the existence of a boundary layer that emerges as fluid flows through and around solid objects. So if I have flow through a pipe, which is what we deal with like 80% of the time, we're going to have these several boundary layers that emerge, where we have this laminar boundary layer. It's also called a viscous boundary layer. Then we have this transitional boundary layer, which is also known as a buffer layer in your text. And then you have this fully turbulent boundary layer, which it's considered part of the boundary layer primarily because it interacts with the other two boundary layers. And so, independent of what the actual average flow regime we have, we still have the existence of all three flow regimes along the surface as a function of the interactions that occur with the solid and the fluid interface, right? So we have the sticky interface that results in this no-slip condition. And as a result of that, we have viscous flow very close to the solid fluid interface. Then as we move away from the solid fluid interface, we have more indicative flow of what you would expect of the bulk flow, which means the flow regime's changing as a function of this, y direction, even though fluid is flowing in the x direction. And so what this means is we have a lot of different flow regimes at, flow at varying velocities, all within the pipe system or the flow system. And this results in a lot, especially in a buffer layer, we have a lot of mixing, but at the same time, close to the solid fluid interface, that means we have a lot of shear happening due to the viscous flow that's occurring. And so if we're gonna look at flow through a pipe and we wanna categorize shear, if, these are my two pipe walls, I know they're thick pipe. It's all Home Depot had today. And if I wanted to categorize the magnitude of shear, what you find more often than not is that our shear rate, and if this is the direction of flow, shear is going to resist that flow, so it's going to go in the opposite direction. The maximum shear stress that we see within our fluid flow is going to be at that solid fluid interface as a function of that no-slip condition and the viscous flow that happens very close to that. Then as we move into the center line, our shear diminishes such that we can say there's really no shear at the center. And at the same time, if we look at if this is shear and this is velocity, we have a minimum velocity at the surface, right? We have a no slip condition, and we have a maximum velocity at the center line of our flow. Now the actual nature of the curve, or I'll just draw it like a parabola here, but the nature of that curve is largely dependent on the bulk flow regime. So they'll say the bulk flow regime determines u of x, or velocity. Actually, that's going to be u of y. Velocity as a function of your placement along this y coordinate. Or if we're looking at a laminar flow regime, you're going to have something that's very parabolic. If you're going to have a turbulent flow regime, so this would be more indicative of laminar flow. If you're looking at turbulent flow, I'll draw it to the right here, even though it's probably not going to help you much. You have something that looks a little more like this. It's a little more flattened out. And so you can kind of tell that this variation from the mean is largely shows you kind of where the existence of that boundary layer is. Which means in general, the lower the velocity, the greater the effective boundary layer penetration depth. But that's not super important as of right now. The important thing I want you guys to kind of get is, the no slip condition and how that kind of leads to the formation and existence of these boundary layers, be it the laminar boundary layer, the transitional boundary layer, and then the turbulent boundary layer.
I have a question.
Yes, sir.
You said that the turbulent flow has all three. Does the laminar flow have turbulent flow inside of it?
If you're looking at truly turbulent flow, you're not going to have turbulent flow boundary layers. No. It's only when the velocity is sufficiently high. And if the bulk velocity is so low that the flow is largely considered laminar, you're really only going to have laminar boundary layers.
Okay, thank you.
You're welcome. That's a good question. And so a couple things to calculate from this. One is let me see what I calculated. The distance to transition from the laminar to a turbulent flow in the boundary layer. And what that means is if we're looking at this formation of the boundary layers, I drew this kind of intentionally because the boundary layer emerges kind of like along this gray line it's a little hard to see. So I'll just kind of color it in. And so there's a distance, which we can kind of denote as x, where the boundary layers that are formed are largely laminar in nature with some transitional. Once you start to see the formation of a turbulent flow in that boundary layer, we characterize it by this transition length, where we can say that the boundary layers are are considered fully developed. And so we quantify it by this expression. So we have the Reynolds number of our fluid flow, the flow velocity, flow density, and flow viscosity. And then X is that transition length as terms of when that boundary layer is going to be considered fully developed. Another transition length and I know they're confusing because they're both kind of transition lengths. It's the entrance length where the boundary layer or the influence of the boundary layer reaches the center line. Which means, if we're going to describe this, if I've got flow through a pipe, when I'm looking right at the entrance of a pipe, I'm going to have my flow all having the same mean velocity as a function of that y coordinate. But as I enter, I'm going to start to see the boundary layers start to form within my flow system. And so essentially the distance or the transition length for that velocity profile to fully develop is going to be characterized by a second transition length, which this one is going to be 0.05 times my Reynolds number times my pipe diameter. And I would argue this one's more important than the other transition length, primarily because we're going to see this one again when we look at heat transfer later on in the semester. So let's look at an example of this, where I can say estimate the transition length at the entrance to a 15 millimeter tube where glycerol at 60 degrees is flowing at a velocity of about 0.5 meters per second. The density is 1,240 kilograms per cubic meter, and the viscosity is approximately 0.0822 Pascal seconds. So I'll give you all a second to write that down. All right. So you guys get that written down?
Yes.
All right. So rather than me working the equations again, I'm going to shoot you all into some breakouts so y'all can talk amongst yourselves and practice together. So I'll give you all a few minutes, probably 3-4 minutes to jump into the breakouts and work together to solve the problem. Then we'll come out and talk about it before we move on to our next topic. How's it going in Laham?
I'm good, Dr. Lopez. I'm just a little bit sick. How are you?
I'm all right. I'm sorry. Are you ill with a stomach bug, a flu?
No, I took the COVID test yesterday. They told me to quarantine myself until tomorrow, that they'll give me back my results.
Oh my goodness, I'm sorry.
Yeah.
Were you in contact with anybody, you think, or you just?
No, but like I've been sick since like Thursday, Friday. So my sister like pushed me to get tested. So if I actually have it, not go to school, then like not affect anybody else. So
That's probably a good point. It's better to know
Yeah.
than not.
yeah, they told me that if I test negative, I have to go in and test for strep. They told me you have something, but just
Well,
wait
let's hope
to see
let's hope
what it
it's
is.
something a little less intensive as COVID.
Yeah, hopefully.
Have you been on campus at all?
Yeah, I've been on campus every day kind of since May. I go to lab, but I don't know, like this past week I went to like the Rebel Market twice, so maybe it was that. I don't know, honestly.
That's not good. Well, I hope you feel better soon.
Thank you, thank you.
Give everybody a couple more minutes. This is so weird teaching a class in two different formats.
Yeah, it's a new experience, I guess.
Yeah, especially because when you're teaching two sections of the same class, you're just repeating yourself and you feel like you're going quite crazy.
Yeah, I guess so.
Are you taking any classes this semester or are you just straight
Yeah,
research?
that's my last class. I'm taking DOE with Dr. Nooranian.
Oh, how's that?
I really like the class. I wish I'd taken it my first semester, not my fourth, but
Yeah, it's a really helpful class for new students in terms of how to think and design experiments well.
yeah, because I had like a little bit of an issue with like variables and all. So I wish, like, even Dr. Smith told me you should have like taken DOE sooner, not to like face these kind of issues. But it's just every 2 years, so.
All right, I'll see if I can bring everybody back. I like the breakout rooms. Welcome back.
Thank you, thank you.
I like your background, Dr. Lopez.
Yeah, nobody's yet to guess where it's from. I should offer bonus points if somebody can guess what it's from.
Shut the fuck.
Is it from Thor or something?
No,
No, it's
No.
not.
Okay.
Not Star Trek.
nope.
Battlestar Galactica, maybe? I don't know.
Mm-mm.
I'm just naming all the sci-fi movies I know and shows.
It's something deep no one would have seen. It would be like that recent Fantastic Four movie. Just one that was so bad no one saw it.
It's actually not from something recent. It's from something unfortunately older.
Space Odyssey.
Not that old.
2002. Not that old.
I'm older. I'm not that old.
Yeah.
So how did the problem go?
Wasn't too bad.
All right. What did you all get?
.08485.
Okay, so about 85 millimeters.
Mhm.
Right, so not a huge transition length, but I'm pretty sure that one was a laminar flow, if I remember correctly. So that's good. So I think with that, I'm pretty happy with our discussion on flow regimes. One last thing we can discuss is the last question I have for the day. Is this example: if I have air at 3 atmospheres at 100 degrees Celsius, flowing at 1 meters per second in a small tube, and if I estimate that the flow is laminar but nearing turbulent, which of the following would cause the flow to become more turbulent? Would it be A, increasing the air temperature, B, increasing the tube size, or C, increasing the air pressure? So I will give you all a second, and we can play everyone's favorite game, paper, scissors, rock. So if you think that the answer is A, you can show me paper or rock, whatever this is. I know it's Tuesday. Or you can put it in the chat. B, it's increasing tube size, and C, increasing the air pressure. That would be scissors. So are you guys ready to play the world's most exciting game? Brady Bunch, paper, scissors, rock. Ready? Paper, scissors, rock, shoot. All right, I got some papers in the house. Confident rock. I got a pen. I'm not sure what pen means. And then I got ghosts from anybody else. I have this problem where I don't see dead people, I just see names in black. All right, so the answer, I got 2 people from the chat. Paper, I like it. Everybody's a fan of paper. The correct answer from this is it depends. I know, everybody's favorite answer. Jacob's over there about to throw his computer at me. So let's take a look at this one. So if I'm going to go from a laminar regime to a turbulent regime in a gas, and do I increase the temperature, the pipe diameter, or the pressure? Well, if I increase the temperature, well, since it's a gas, and I know Reynolds number, and I know we're not going to talk about mass velocity for much, increasing the temperature is going to decrease the viscosity, which means that's going to make it more turbulent. However, if I'm increasing the temperature, knowing that the density is a function of temperature as well, my density is going to decrease as well. And so the only quote unquote incorrect answer I would argue is temperature. So this is, I have to put an X on this one. In terms of the diameter, that's a valid answer because increasing the diameter is going to increase the flow area, which is going to increase our flow. However, the issue is here. If we increase the pipe diameter or diameter flow, and we're not increasing anything in terms of flow rate, that's going to have an impact on flow velocity. And so as of now, we haven't gotten there yet. We're getting there next. I would say, okay, I give you that answer. And then the last one would be pressure. Increasing the pressure would, by the same ideal gas assumption, increase the density It's not going to change the velocity, diameter, or viscosity. So that would increase the Reynolds number and move us into a more turbulent regime. So I'd say this is like a 3/4 check, and pressure would be a full check. So there you go. The answer is it's not as simple as paper, scissors, rock. As much as we would like to assume all of life's greatest mysteries can be answered with just paper, scissors, rock. So any questions over our discussion of flow regimes? All right. That means we're ready to move in to some of my more favorite topics in fluid mechanics. Mass and energy balances. In fluid mechanics. I like them so much, I'll draw a really creepy smiley face. So, everybody's favorite, mass balances. And we can describe a lot of really complicated math, which we'll get to in a second, but it all boils down to a very simple life lesson. Garbage in equals garbage out. So the question then becomes, how does this apply to fluid flow?
I was on the early one, but I can't see the notes, and it's still on the PowerPoint for me.
Oh, it's still on the PowerPoint for you? Okay, thank you for letting me know. All right, so you missed out on my fun smiley face. There it is. So looking at mass balances, we'll probably do energy balances on Thursday. So how can we apply this to fluid flow? Well, let's say I've got a cube, which I will attempt to draw and have it not look terrible. And so I've got fluid, and I'm looking at just one section of this fluid in terms of it being a cube. So I've got mass coming in, and I have mass coming out of this cube. And that mass can be characterized in terms of flow density and a flow velocity in the x direction. And so this cube is a delta on each side. I have a delta y here, delta z here. I've got x, y, z. I can categorize the flow thusly, where I've got flow going in, flow going out. Now I can do this for every coordinate on this cube. Meaning if I wanted to fully describe the mass flux through this cube, the equation would look like this. I would have rho ux minus rho u x plus delta x dy dz plus rho v y, and I'm using v for a very important reason, y plus delta y, because I can't say that it's the same flux going in the x and y direction, dx dz plus rho w z minus rho w z plus delta z dx dy equals delta x, delta y, delta z, dp, dt. Excuse me, this is d rho dt. Got to make sure my pressures and densities. So this quantifies my max flux in all in x, y, z directions over a differential volume element. Now, who wants to solve this? Claire, it's d rho dt, not dp dt. So the good news is I can summarize this differential expression by taking the limit as dx, dy, and dz approaches 0. And what I'm left with is a more straightforward expression of d rho dt equals negative d rho u del x. Now these are partial derivatives, plus del rho v del y plus del rho w del z, which can be summarized by a fancy math operator known as the gradient times g rho v. And for those of you that like to know, this is equation 4.3. So a partial derivative of density with respect to time is equated to the gradient function of the density over the volume element that we analyze. All right, I will do Elijah, thank you. So while pretty and mathematical, this isn't going to be super helpful for us, which means we can make some assumptions. And one of the most powerful assumptions that we'll make for most of this is that we're going to assume one-dimensional flow. Doing this allows us to drop out two of those three coordinates. And we're left with something a lot more simpler, where we have dm dot is equal to rho u ds, which is simply the differential mass flow rate is a function of the fluid density, the flow velocity, and the differential cross-sectional area. So if we integrate this from 0 to s, actually, you know what? I'm going to do something that makes way more sense because this book is silly. 0 to A. I'm going to call it cross-sectional area A because area starts with the letter A, and that makes way more sense to me. So we're left with M is equal to rho UA. And more importantly for us, I would state M1, rho 1, all right, let me take a step back because I don't want to confuse anybody. So we have this expression, M is equal to rho UA, which means if we're looking at flow through a pipe, and I have some mass flowing in here and some mass flow flowing in here, and I wanted to take a mass balance of the flow through a pipe, what expression would I get? Just in terms of these mass flow rate variables, M1 and M2.
Would it be that M1 equals M2? Is that what you're asking?
Yes. So I would get M1 is equal to M2, or garbage in is equal to garbage out. I know we had to do a lot of calculus and differential equations to get where we started. That's how math works. Which means, based on the expression I derived, rho 1, U1, A1 is equal to rho 2, U2 times A2. Now this is a very important equation. I repeat, this is a very important equation. So much that we give it a name. Not only do we give it a name, we give it all the fanfare that we can imagine. You know, I don't know what else you want for me to let you know this is important. So I'm going to give you all the colors. You know, I'll even give you a highlighter. So if you were going to have an equation sheet, this would probably be an equation I would put on it. So if we're going to describe flow through a pipe, one of the important principles in terms of this mass balance is understanding the implications for the continuity equation and applying it as it relates to flow systems. What do I mean? Let's take a look at an example. Oh, hold on. I have to open up the PowerPoint. Because this class is so advanced, we're looking at 2 PowerPoints in one day. So let's look at this system. So say your friends over in civil did such a bang up job in their internship that they somehow managed to make a pipe with a decreasing diameter over the length of that pipe. Makes a lot of sense if you know some of those people. So how would velocity change as the fluid moves along the pipe? And how would the flow rate? So let's jump back to our notes. So example 1, civil engineers. ... That's all I need to say, right? That's usually how they spell it too. All right, so we got flow through a pipe. We've got diameter 1, flow through a pipe, diameter 2. And I've got some mass flowing in, and I've got some mass flowing out. So what can we say about the flow rate? Let's start there. M1, what? Is it equal, greater than, less than M2?
Equals M2.
So M1's going to equal M2. Okay, that's great. So what's going to happen to the flow velocity? Well, I have rho 1, U1, A1 is equal to rho 2, U2, A2, where density, velocity, cross-sectional area. Keeping in mind, and for now, A means cross-sectional area. Later on in the semester, it might mean surface area, but we'll cross that bridge when we come to it. It's a problem with engineering. We only got 26 letters in the alphabet, and we've got about 4,000 engineering variables we have to discuss. So let's start off with density. Is density going to change?
No.
Okay, so we're going to assume rho is constant. And when is rho constant? What kind of fluids?
Incompressible.
Incompressible flow. Now you're speaking my language. Wonderful. So if rho is constant, I can say I don't care about rho anymore. It goes away, right? Rho 1 is equal to rho 2. They both drop out of the equation like a bad habit. Skadoosh. So now I'm left with U1, A1 is equal to U2, A2. Right? And if I wanted to be real fancy, I could say A1 is equal to pi d1 squared over 4. A2 is equal to pi d2 squared over 4, assuming I'm flowing through some attempt at a circular pipe. Which means if I wanted to plug those in, I have U1 times pi d1 squared over 4 is equal to U2 pi d2 squared over 4. The mathy stuff goes away because we're engineers. We don't want numbers in our calculations. We just want letters. So we're left with U1 times d1 squared is equal to U2 times d2 squared. So zooming out because we have the technology, what is that going to do for our flow velocity? So as I move through that pipe, what is the flow velocity going to do? Is it going to increase, decrease, or stay the same?
It should increase.
The flow velocity should increase. So I can say since D2 is less than D1, U2 is greater than U1 by continuity. Right? So I narrow that flow area, the velocity is going to increase. Really good example of this, I'm sure we've all done at some point of our life, playing in the backyard as a kid, before 2020, Pepperidge Farm remembers. You put your finger on the hose. When you put the finger over the hose, the velocity goes way up in terms of the flow. One more thing I want to leave you with is, okay, let's say your civil engineering buddies talked to you before they did their design. And so you chemies, you fixed it. And so now we've got an actual normal pipe that someone would want to buy, where D1 and D2 are the same. But instead of having incompressible flow, I have compressible flow. I would have the same continuity expression, right? Which means rho 1, U1, A1 equals rho 2, U2, A2, correct? So my areas are going to be the same. So I get rho 1 U1 is equal to rho 2 U2. So if I'm looking at compressible flow, if I have just a simple pipe with the same cross-sectional area along it, my density and velocities are going to be equal. But now what happens if I add friction? Right? And I'll leave you with this thought. I'm not going to answer it today. I'll answer it on Friday. So now I have big P, P1 and P2. If I have friction, I want you to ask yourself, how does pressure change? And how does it influence the expression that we have? Rho 1 U1 is equal to rho 2 U2. So tune in next time. And we'll answer that question together. All right, guys, that's all I have for today. Sorry, I'm a couple minutes over. But if you have any questions, I'll see you in office hours. Any last minute burning things? One thing before you jump off, the grader asked me to remind you, please limit your significant figures. I know you all think you have the world's most powerful calculators, but we don't need 6 to 8 sig figs on your answers. Like I said, just keep it simple, okay? All right, guys, take care. Have a great day.
Have a good day, Dr. Lopez.
You too. Take care, Claire.